Latitude Media, covering the new frontiers of the energy transition.
I'm Shayle Kann, and this is Catalyst.
There are markets for each one of these chemistries within the EV market alone.
Coming up, it's been a while since we did a good old-fashioned battery technology deep dive. So here we go.
Do you want instant access to energy storage supplier pricing that's project-specific? Or the ability to compare domestically made battery and PCS options across the market? ANSA now offers the industry's first battery energy storage data and analytics platform to make better development and procurement decisions. ANSA provides in-depth commercial, technical, and risk data and analytics to help developers choose the best equipment for any project. Improve your returns and save months of evaluation time with ANSA. Learn more about ANSA's energy storage subscriptions at go.ansarenewables.com/latitude or click the link in the show notes.
Imagine a world where connected devices like EVs, home batteries, and smart thermostats work together to support a more efficient and reliable power grid. Well, you don't have to imagine it anymore. This vision is a reality today thanks to Energy Hub. With Energy Hub's Edge DERMS platform, utilities can create virtual power plants through customer-centric flexibility programs, making it easy to manage distributed energy resources and balance the grid. Unlock grid flexibility and reliability through cross-DER management with Energy Hub, the trusted Edge DERMS leader. Visit energyhub.com to learn more.
I'm Shayle Kann. I invest in early-stage technologies at Energy Impact Partners. Welcome. So as you know, I'm a venture capital investor in early-stage deep technologies for the energy transition. And so, as is true of many of my peers, I've taken many pitches for new EV battery chemistries. There are two big challenges with this category from a startup perspective, in my humble opinion. The first is just how hard it is to penetrate. The timeline, the capital intensity, the requirements of the vehicle OEMs, who are your ultimate customers if you're trying to build one of these businesses, they all present this nigh impossible gauntlet to cross for a startup. Second, though, to a first order, virtually all of these battery technology pitches kind of sound the same, at least on their surface. They promise better performance at lower or equivalent cost. Lots of upside, no downside. And so it becomes a little bit of a blur. But what stands out to me, at least, is when one of the major players in the market announces their own innovation in similarly breathless terms. So the title of GM's blog post in May was, quote, "Why LMR batteries will change the outlook for the EV market." All right, so that seems worth understanding. So I brought on Kurt Kelty, who is GM's VP of Battery Propulsion and Sustainability, to talk it through. Kurt is also a longtime battery supply chain expert. He worked at Sila Nanotechnologies. He worked at Tesla before that. So I wanted to spend some time with him talking more broadly about the state of the North American EV battery supply chain. Also, before we begin, I'm hosting, I think, my third Ask Me Anything episode, maybe fourth. Anyway, I will answer all of your questions, big and small, about technologies and the energy transition, markets, venture capital, investing, something cool, something boring. Come at me. If you want to ask a question, just email at catalyst@latitudemedia.com. That's catalyst@latitudemedia.com. For now, here's Kurt. Kurt, welcome.
Glad to be here.
Glad to have you. I want to start talking at the high level about the state of manufacturing for batteries in the United States, and then get a little bit more into detail on this new battery chemistry that you guys are pioneering. But starting at the high level, I guess, how would you characterize where we are in terms of the journey to be able to manufacture EV batteries here in the United States?
I would say we're at the early stages of this. I joined the battery industry about 30 years ago, and at that point, we were moving all the manufacturing offshore to Japan. And I ended up leading the effort at Tesla to bring Panasonic along the ride and to bring cell manufacturing back to the U.S. And at that time, we built the Gigafactory. It was going to double worldwide production with the first factory that we put in place there. And we were successful with that. That was kind of the first real deployment of battery manufacturing back to the States with lithium-ion cells. And since then, Multiple companies have got into it, whether it's LG, Samsung, SK, and many of the Chinese as well. So our manufacturing in the U.S. right now, I would say, is a very early stage. All of us are getting started. Panasonic's got a couple of years ahead of us because of that gigafactory that we put in place. With Ultium cells, we started producing in high volume about 2 years ago, and we're pretty much the second ones right after that. So we've got 2 factories right now producing. The capacity is roughly 40 gigawatt hours at each factory. So they are significant high volume manufacturers. And we're now at a point where we are the largest OEM producer of battery cells in North America with these 2 factories. We're adding a 3rd factory, Synergy. It's a joint venture with Samsung. So we'll have 3. Then that one goes online at the end of 27 in Indiana. So we'll have 3 factories at that point, roughly all of them having about 40 gigawatt hours per year capacity at each one of them.
You mentioned a couple times cells. I guess walk me through the value chain for a second, starting, minerals, materials, precursor materials, et cetera, cells, packs. Like, where do we have the most domestic supply in that supply chain, and where do we have the least?
Yeah, no, it's a good way to look at it, because what you want to do is you want to manufacture as close as you can to the end product being an EV. And so you want to manufacture the battery packs as close to that as possible, because it's just it's prohibitive to ship. It just gets very expensive, the packaging, the logistics cost of that. Then, of course, you want to do the module here locally as well. So those are kind of 2 right from the beginning. You got to do the module and pack domestically if you're going to be producing EVs domestically. Then the cells ship better than others. So you could actually manufacture the cells elsewhere. We are manufacturing for all of our vehicles. We've got 12 EVs on the road right now, which is more than any other EV manufacturer. And all of those cells come from our Ultium cells in North America. So we produce all of them domestically. Now, when you go back up the supply chain further, the big materials next are the active materials, the cathode and the anode. The anode right now is almost 100% from China. They make graphite, both the artificial and the natural graphite. So that comes from China right now. The cathode material, that is a little bit more diverse in the sense for us, it's coming from Korea right now, and it's going to be, and each one of these materials will be more localized going forward. But right now, if you were to say, where is the value stream? So the cathode materials coming from Asia, and then before that, you've got the precursor material. Before that, you've got the nickel sulfate, the manganese sulfate, cobalt sulfate. Those are all coming from Asia. And then you actually have the minerals. So the nickel, the cobalt, and the manganese. The nickel primarily is Indonesia right now, is where it's coming from, as well as China, as well as there's multiple other countries. Canada makes a bunch through Vale. So there's a bunch of locations, but Indonesia is really leading that right now. Cobalt is generally from the the Democratic Republic of Congo, and you're getting more and more companies like ourselves that are trying to reduce the amount of cobalt in the cells. So that comes from Africa, and the manganese is from multiple locations. But nickel is generally Indonesia, and that's the high value item. And then the last high value item is really the lithium. And lithium reserves are around the world. We've got a really large a number of reserves in the U.S. In fact, we've invested a lot in this. So Lithium Americas is a company we've invested several $100 million in already. So they're going to be producing in the U.S. They're coming online in the next couple of years. But in general, what we're doing is this supply chain is getting more and more localized. So between now and 2028, we're going to localize the supply base by about 8-fold between now and 28. So we're putting a huge amount of emphasis on trying to bring that supply chain into North America, U.S. if possible, but North America is what we're going for. And we're making investments. We're putting money behind our talk. As I say, we've invested in lithium. We've invested in manganese production as well. We invested in graphite, bringing graphite to North America. So we're putting a lot of money in this to bring the supply chain more local.
I'm curious what the high-level theory of the case is for you on when it does and doesn't make sense to onshore or nearshore, for that matter, various steps in the supply chain. You mentioned one element of it, which is it becomes prohibitively expensive to ship modules and packs. And so there you've got what I imagine is a pretty straightforward calculus around the different costs of production versus the additive cost of shipping. Now, of course, there are a million confounding factors here in the U.S. with regard to tariffs on China and all other countries, possibly the existence or non-existence of Inflation Reduction Act related incentives. Set all that aside, maybe, because I know a lot of the decisions that you've been making predate that. What do you think of as the factors that are determinant in whether it does or does not make sense to onshore manufacturing at whatever step in that value chain?
Yeah, it's a theoretical question because we don't live in that world where there's no tariffs and there's no incentives. But let's go to that world because I think it's valuable to have that discussion. So if there were no tariffs, no incentives, then I think you would go to the place that is the most economical to produce, and where the most economical to produce is generally where the material comes out of the ground. Depending on how far you go, because the processing, it doesn't make sense to ship rock from Indonesia to the U.S. to do processing here. So you would process it in Indonesia for the first stages. And then what you're going to do is once you get the nickel from that, you're from the mountainside there, you're going to get nickel, and then you need to make nickel sulfate. Nickel sulfate is predominantly a liquid. You don't really want to transport that because it's not the percent nickel is just too small. So you'll make the precursor material on site. There is what you would normally do with rational actors. That's what they would do, and then you would most likely ship that precursor material, which is a powder, and you'd send it in these big super sacks, and you'd send it to a facility to make cathode material. Now you could make cathode material at the same location, but you also have to combine that nickel sulfate with some of the other materials, including the lithium, when you're making up the cathode material. And so you've most likely need to find a central location to do this. Other countries in Asia could be appropriate. For example, Korea, Japan could be locations where you would do this. It could be also in North America. And that's the direction that we're going with local production of cathode material. So we're working with partners here to manufacture that locally because that makes good economic sense. You send the precursor material over here and then you take that precursor and you make cathode material. Now, if you want to become less dependent upon the supply chain coming from Indonesia or coming from Korea or Japan, you could also make the precursor in North America. The challenge with that is that it will most likely be more expensive because our environmental rules are tougher. The concentration from the mountain may not be as great as what we're going to get in Quebec, for example, for nickel. So there's multiple, there's a lot of different moving pieces here. And then when you put the tariffs and the incentives in place, then it changes this all around. Like if you're really trying to encourage domestic production in the US, you would put in tariffs to increase the cost overseas, and you'd incentivize local production. The problem with that is that your costs would end up going up higher, and your EV prices would end up being higher. You'd stifle the EV demand, and that's not accomplishing what you want to accomplish. So it's a really complicated, with multiple dimensions here, to really figure out exactly what is the optimal strategy. And this is what we're trying to do this at GM right now, is trying to figure out what is the optimal strategy. With you got movement on tariffs, you got movement on the PTC, the incentives. They're going to expire in 2031 or 2032, and you want to build up a supply chain that is also economic after that. after those incentives go away. So there's a lot to think about here in trying to set up the optimal supply chain for batteries.
Catalyst is brought to you by ANSA. ANSA offers a one-of-a-kind data and analytics platform and advisory services to support better project development and procurement decisions. For energy storage developers, ANSA's platform provides crucial information that you never had easy access to before. Now at your fingertips is real-time pricing for a long list of system configurations to suit any project. ANSA provides a 360-degree view of the market with lifecycle cost analytics and commercial, technical, and risk data. With ANSA, developers can easily determine which products to use in their designs, finance models, and RFPs. Learn more about how ANSA helps save time and maximize profit at go.ansarenewables.com/latitude.
Catalyst is brought to you by Energy Hub. Energy Hub helps utilities build next-generation virtual power plants that unlock reliable flexibility at every level of the grid. The Energy Hub platform takes the guesswork out of balancing energy supply and demand. It uses machine learning to control customer-owned distributed energy resources, like EVs, home batteries, and smart thermostats, to precisely shape load profiles for grid flexibility and reliability. As the industry leader, Energy Hub helps more than 80 utilities manage 1.6 million devices. That's more than any other edge DERMS on the market. Click the link in the show notes to learn more or go to energyhub.com.
All right, shifting over from supply chain to battery technology itself. So you guys put out an announcement at GM, a month ago from this recording, maybe a little bit more. That was, I would say, for corporate blog posts, pretty breathless and excited. It came through, focused on this cathode chemistry that you are commercializing called LMR. So give me the context and the background here. I mean, folks know, I think, who are listening to this, NMC and LFP maybe at the high level, but walk me through LMR, the history, and like why it is so exciting to you.
Yeah, this is super exciting for us because it enables us to lower the cost and maintain high performance. And what we were trying to do, so over time, NMC has been the chemistry of choice in the Western world for EVs. And that's a mixture of the N stands for nickel, the M for manganese, the C for cobalt. And when EVs first came out, when we were doing this at Tesla, when I was there in 2006, we were buying cells that were basically 1-1-1. 1% nickel, same percent cobalt, same percent manganese. The problem was that the cobalt was the most expensive. So what we all tried to do is reduce the amount of cobalt. And we did that. As the industry, we reduced that. And the new chemistry of choice became what we called high nickel. So that was majority of nickel. When we say majority, it went from 60% to 70%, 80%. Even nowadays, you're up to 90% nickel. So it's mainly nickel, and you got a few percent cobalt and a few percent manganese. Now, what we wanted to do was take the next highest material cost, which is the nickel, and we wanted to reduce that. And so that's what we've done, is we've reduced the nickel way down in the amount we use, and we fill it in with manganese, which is really cheap. Manganese is like $2 a kilogram. It's really cheap to buy manganese. And so by doing this, we reduced the cost. Now, what we were able to achieve, though, was we're able to maintain a really good energy density. Now, it's not as good as the high nickel, but it's in between that high nickel and the LFP in terms of energy density. So, for example, when you look at it, let's take one vehicle, the Chevy Silverado. This is an EV that gets over 490 miles of driving range, the best on the road of any truck out there. You take that, and you can get that with high nickel, that 490 miles. Now, if you put LFP in there, you're getting about 350 miles of range. Same battery pack, same size and all that. It's the difference in energy density. So you'll get 350 miles. Now, if you do NMC, you're going to get 400 miles of range, but you're going to get it at the LFP pricing in terms of dollars per watt hour. So that's the advantage, is that you get something in between there in terms of your driving range, but you're able to do it at the cost of the LFP. And that's what's really exciting for us.
Is there a case here that, look, if the promise of LMR is it is a near NMC level energy density at LFP cost, I mean, setting aside the EV market for a second, which I know is where you're focused, the stationary storage market, that is dominated by LFP. And energy density is not as important in stationary, but it's important still because the balance of system costs and site costs and all that scales with size. Is there not an argument that you should be also going after the stationary storage market and trying to basically swamp LFP in that market? Or is there a downside or a trade-off here with LMR that would make it less attractive in stationary?
So I like to talk about batteries in terms of trade-offs. So I'm glad you used that term, because what happens, and I've seen this so many times over my years, is you get this announcement from A company or B company, and they're like, "Oh yeah, we've got the best."
We did it. It's solid state. It's whatever.
Yeah. And they announce this thing, and what happens? They leave out one or two metrics that are kind of important, like they leave out cost, or they leave out cycle life, or like a fast charge rate, or whatever it is. They leave out something, and the beauty of LMR is that there are no drawbacks to it in the sense that it has good energy density. It's not as good as high nickel. So I want to be clear, it's between LFP and high nickel. But all the other characteristics of the chemistry are all solid. So it's not a trade-off chemistry. That's the beauty of it. Now, when you're going though to a different market. So I'm talking, there's no trade-offs for the EV market. But if you go into the ESS market, the energy storage market, what's required there, they're looking for 10, 15, 20 years of storage. They're looking for it to be cycled every day. So you can do the simple math. You got 10 years, that's 3,600 cycles that you need to get on the battery cycle. You do 20 years, you double that. Now, in vehicles, generally 1,000, 1,500 cycles is considered sufficient for the lifetime of the vehicle. But if you're looking for something that's much greater cycle life, LFP is really good for that. LFP has got really deep. I mean, you obviously have to optimize the chemistry for it. You can make an LFP that's optimized for reasonable energy density and cost that doesn't have great cycle life, or you can optimize around really good cycle life. And you can pay for it, whether it's hard carbon you put in the anode or something like that. You pay a little bit more for the anode, but you're getting much greater cycle life. So LMR is good for some energy storage applications that are cycling periodically, that are cycling 30 times a year, 50 times a year, something like that. LMR would be great for that because you'd have a smaller footprint that would be required for it compared to LFP. But if you're looking for something for 20 years cycling every day, LFP is still the preferred chemistry for that.
Okay, so then back to the EV battery world. Why? I mean, LMR, you didn't invent LMR. It's been attempted for decades, a century. I don't know, you tell me. Probably less than a century. But why has it been tough historically?
Yeah, this was started probably about 20 years ago in Jeff Dunn's lab at Dalhousie University in Canada is where they started it. And then Argonne really took it to another level. And then it was kind of parked for a long time. And I know Professor Don has come back to this a couple of times looking at it, but they just haven't been able to solve some of the technical challenges that were there. And our team's been working on this for about a decade overall. And one of the beauties of being a EV manufacturer and now having the lab capabilities that we have at GM now is we can prove out our own technology and figure out how it's going to work in the vehicle. We've invested over the years in really state-of-the-art equipment for our R&D labs. And then about 2 years ago, we opened up the Wallace Center, which builds large-scale battery cells. So they can do a large 200 amp hour pouch cell or prismatic cell or whatever we need. And we can actually do testing on it in an auto scale size and put it under the test of what our automobiles would see in the real world. And so we were able to do this. So we did work in the R&D lab. Then we pushed it up to our Wallace Center to build the full scale cells. We tested it under the variety of conditions that it would have for a vehicle. And then we worked very closely with our partner, LG Energy Solutions, and got on board with them such that we all agreed, well, this is an excellent solution for an EV truck or a full-size SUV. It just fits in there really well. The energy density is, because we've got more space to work with in a full-size truck and a full-size SUV, it doesn't need to have that amazing energy density because you got space to move around in there. You want it to have a really good range, but you're really driving down cost. And that's what enabled us the LMR enables us to drive down that cost while maintaining that range.
You mentioned that historically it's been difficult to overcome technical challenges. I want to dig into it a little bit more just because I feel like battery manufacturing is notoriously hard, but a lot of people just don't understand what the actual problems you run into are. So can you give me an example? What exactly made it hard to do LMR? What was the technical hurdle you had to overcome?
So yeah, batteries are really, really hard. And I've gone on, so kind of starting back in my days at Tesla, when Elon wanted to get into cell manufacturing. And I really argued that, no, we shouldn't do that. Argued with him the second time, we shouldn't do that because he really wanted to get into cell manufacturing because no one would listen to us and build enough cells for us. And finally, I was able to convince them, yeah, let's do it, but let's do it with Panasonic. And so I brought Panasonic along, and Panasonic actually built the cells in the Gigafactory. If you look at what we've done at GM, is they recognized that early on also that building cells was really hard. And so they partnered with LG. This is before I came here. And it was an excellent decision to make to partner with somebody that knows what they're doing. And so we have 50-50 joint ventures with LG. Now, if you look at another example, Northvolt in Germany, how they tried to do it independently. And we all see what happened in that case. It's really difficult to make cells unless you have that expertise. So we were able to make our cells in the lab. We were able to overcome some of these technical challenges that had made it difficult to bring this to commercialization. And then we were able to partner with LG and actually put it into their pilot line and to show that it worked. And that was the big thing, is to be able to take some of the work that we had done, combine that with LG and the work that they had done, and then manufacture it in a pilot line and prove out that, hey, this will work. It'll get us the cycle life we need. It'll get us the energy we need. We can manufacture it at an economical cost. Let's do it. And then we pulled the trigger.
But just to pin you down, can you give me an example of a technical challenge?
One of the challenges we had was on cycle life. And how do we solve for that? Because initial cycle life just was not proving to be good enough for what we needed. And so we had to go back and figure out, okay, how are we going to solve this for cycle life? How are we going to solve for formation time? Because formation can take a really long time to do. And formation is kind of the last finishing process that you have to do before you start shipping cells, before they're ready for usage. And one of the things is, if you have a really extended formation time, then it kills your cost. Because everything that adds time in the production process just adds cost. And so these were some of the issues that had to be dealt with that our team was able to figure out, okay, let's figure out a solution and work with LG and put this into production. So those were two of the issues that we had to deal with.
How do you manufacture LMR? Is it drop-in for existing manufacturing? Do you need to stand up entirely new lines, entirely new factories? What does it look like?
So this is one of the beauties of LMR, is that it really piggybacks off all the work that we've done with high nickel. So it's the same manufacturing process. So we'll use the same Ultium factories. It's the same electrode manufacturing process. The packaging is all the same. The formation steps are a little bit different, but again, the equipment's the same, unless you change the form factor. So that's on the cell side, but what's more critical is what you referred to earlier when you're looking more upstream at the material supply, the supply chain. It's the same players. It's the same company that we're buying the same companies that we're buying the high nickel cathode from can make the LMR cathode as well. And they use the same equipment for it. Right now, there's surplus capacity on the market right now. So there's plenty of capacity to make the new cathode. You drop out a couple of steps there, so it makes it easier and cheaper to make. So you're using the same supply chain, using the same materials. You're still getting nickel. There's still about 1% or less of cobalt, and then there's manganese. You need more manganese than before and less nickel. The anode is still, you're relying on graphite, whether it's artificial or natural graphite. So it's really the same supply chain. It really is a drop-in solution, and that's the beauty of this.
Do you think this is the end of the line? I'm always asking, when it comes to battery chemistries, like there's always the next thing, or at least there's always the promise of a next thing. Are we going to be continually evolving EV battery chemistries forever? Or is there going to be ultimately a winner, and then everything we're doing is just optimizing that winner from a chemistry perspective?
There is going to continue. I mean, we're going to continue to evolve over time. There's going to continue to make this advances are continuing year after year. I mean, we can see over the next 5 years some of the improvements that are going to be made, and then you look beyond that. Of what's going to happen. I mean, we've got silicon coming down the pipeline that's really going to alter the anode landscape. The cathode side, right now, we're at the very beginning of optimizing LMR. You can imagine with LFP. LFP's been around now for 20 odd years. It's been commercialized. They've come down that cost curve over time. And so there's not a whole lot of improvements that you can make with LFP. You got to jump to a new chemistry. With LMR, we're starting at that top of the curve where we're going to head down that cost curve. So there is a lot of future potential with LMR. There's a lot of future with silicon, as I mentioned. We're continuing. We've got an R&D lab that really works with all the leading cell developers or battery developers and tries to figure out, okay, what is going to be the technology 5 years from now, 10 years from now, and we work with them. We're not trying to invent this ourselves. We're trying to leverage what's out there with the startups in the States. You can imagine there's a lot of solid-state companies. You and I have been hearing about this for years. We're not doing solid-state R&D within GM. What we're doing is we're evaluating and leveraging all those startup players that are out there. And the major manufacturers, like Samsung's a big solid-state developer as well. So we're leveraging what they're doing and trying to figure out when is the optimum time to introduce that, and how does that compare with NMC or LMR? What if you add silicon? How does that all look?
I guess the other question is, it's so the promise is that it's higher energy density versus LFP, competitive on pricing with LFP. We've obviously seen LFP prices go all over the place in recent years, but down a lot. There have been all these, like particularly out of China, right? These eye-watering LFP cell prices that get quoted. Do you see LMR as having a similar price floor, not current price necessarily, but similar price floor to LFP ultimately? And I guess the tack on to that is maybe you pointed out the limitations in the stationary storage and the energy storage market to compete directly with LFP. But in the EV market, LFP is being used in EVs too. And there are some ridiculously cheap EVs coming out of China that are all using LFP batteries. So do you see LMR kind of winning that race too, ultimately? Or is it really, should I be thinking about it as like, if you were going to use NMC, now you should use LMR?
No, so I'm glad you're asking this because we want to be real clear. There are markets for each one of these chemistries within the EV market alone. Setting aside the ESS market, if you just look at the EV market, we recognize there is a high range premium market that's out there that will pay for the high nickel. That market's out. You can imagine a Cadillac, the Escalade IQ or the Lyriq or something like that, where you've got customers that are willing to pay for that premium vehicle and that premium experience. Then you've got kind of that middle category that wants good range, but wants to that is more price sensitive. And then you've got the lower range, which is the LFP. So we see a future over the next 5 years where you're going to have these three chemistries, and then you're gonna have some pouch, some prismatic in there. Generally we're going is introducing more prismatic form factor cells in the future because it reduces our part count. Just as an example, the prismatic cells on our next generation pack will reduce our piece count by over 50% compared to our current pouch cell packs. So prismatic cells, so the form factor also plays a big role in this. So we're looking at three chemistries. We're looking at multiple suppliers. We're going to be working with LG and we're going to be working with Samsung, as well as others going forward. So it's really, we've been able to change how we look at this market because we came from this single pouch cell and a single module with the Ultium module, which worked really well to get a lot of vehicles to market quickly. But now what we're doing is we're optimizing each vehicle to try and optimize the performance at the lowest cost possible. And that's why we're going with different chemistries and different form factors to do that. But I see all three chemistries remaining at least for the next 5 years.
So you said over the next 5 years. I guess the final question for you is, when are we going to see LMR batteries in vehicles that we can buy? What's the timeline here?
So we've got a real clear target. Beginning of 2028 is when we're going to start introducing vehicles with LMR. We've got our partner set up with LG. We've already set the recipe for it. We've got we know where the cells are going to be made at Ultium here in the U.S. So that's what and we've got our product already selected as well, where it's going to go into. So we've got a clear line of sight. It's going to be early 28 that we're going to introduce this chemistry, and we're super excited about it because it's going to continue to drive down our costs and maintain really good performance in our vehicles.
All right, Kurt, this was fun. Thank you for the time. I look forward to seeing an LMR battery in the wild.
Me too. I'm really looking forward to that as well. Thank you.
Kurt Kelty is GM's VP of Battery Propulsion and Sustainability. This show is a production of Latitude Media. You can head over to latitudemedia.com for links to today's topics. Latitude is supported by Prelude Ventures. This episode was produced by Daniel Woldorff. Mixing and theme song by Sean Marquand. Stephen Lacey is our executive editor. I'm Shayle Kann, and this is Catalyst.